In this session, we'll study the Scott connection or a T connection. Scott connection. The Scott connection, also called as a T connection, is used to convert a three-phase to two-phase conversion using two transformer. Basically, this Scott connection is used to convert three-phase to two-phase or two-phase to three-phase using two transformers. One of the transformer in this connection is called as the main transformer and other is called as the auxiliary, also called as teaser transformer. There are two transformers, single phase transformer. One is a main transformer and the other one is teaser transformer. They are connected in a particular fashion so that it can convert a three phase to two phase or two phase to three phase. The main transformer must have at least two primary and two secondary coils. Means the primary of the main transformer has got a center tap with the two windings. On one side there is another side and in between there is a center tap. Means it consists of two primary winding, two secondary winding there with a center tap D that I will show in the figure. Means the main transformer must have at least two primary and two secondary coils so that the center tap may be brought out from each side. And at the same time, the teaser transformer must have primary and secondary windings. The number of turns on the primary side of the teaser transformer or auxiliary transformer is 0.866 times that of main transformer. However, the secondary has got full number of turns. That is, the teaser transformer has got a primary winding of 0.866 times the main winding. However, the secondary has got the full winding as per the transformation ratio. The current ratings of the two transformers should be the same. Even though the tappings on the primary of the teaser side we are making 0.866, however, the current rating of both the transformer must be the same. Now we have I told you this is a main transformer. It has got the two primary windings, that is between AD and DB. This is the primary and the center tap as at D, and the secondary has also got two windings, that is between A at this point and B at this center point. This means it has got two primary winding, it has got two secondary winding. Then this is called as a main transformer. Then the same thing is put out here. The main transformer must have at least two primary and two secondary coils so that center tap may be brought out from the each side. This is the center tap. The main transformer is center tap at D and is connected to the lines A, B of the three-phase side. That this is the A, this is the B. I will get the C another point from the teaser transformer. It has the primary winding of AB and secondary winding of small ab. That is, AB is the primary winding of the main transformer, small ab is the secondary winding of the main transformer. Now we have got a teaser transformer. You can see the teaser transformer, the primary has got 86.6% of tapping. It has got only 0.866 times the number of turns of the main transformer. However, the secondary has got the full. You are taking the secondary as a full. At the same time, the primary of the teaser transformer, which is connected to the center tap of the coil AD of the main transformer, it is connected at this particular point D. Therefore, it looks like a T now. It looks like a T. Therefore, it is called as a T connection. It is called Scott connection because it is invented by scientist Scott. Now it is called as a teaser transformer. Now we have got 3 points here for the primary, that is A, B and C. Here we are giving the supply. The sum of the points regarding the teaser transformer are: teaser transformer must have primary windings. Number of turns of which are 0.866 times that of the main transformer, and all number of turns in the second side. There is no tapping in the second side. The teaser transformer is connected to the line terminal C and the center tapping D. That is, it is connected between C and D at the center tapping. It has the primary winding of the teaser transformer is CD, and the secondary winding of the teaser transformer is small cd. That is, AB of the primary winding of the main transformer, CD is the primary winding of the teaser transformer. This small AB is the secondary transformer of the main transformer. Small CD is the secondary of the teaser transformer. Now we have got three input points here, that is A, that is B and C, to which we are giving a three-phase supply. That is the input we are giving. That is, you can see here, that is we have got a three-phase supply. A is connected to R phase, then B is connected to the second phase, Y phase, then point C is connected to B phase. That is, this is A, B and C. This is the input. Then here we are inputting a three-phase supply. Then we are tapping, converting that into the two-phase system. That is, one across AB, another across the CD. We are getting two-phase. There is a conversion of three-phase, two-phase. You can see here. The voltage which is applied to the primary windings are V1, V1, V1. They are all equal magnitude and their phase displacement is 120 degree. Now we have got the primary current of IA, IB and IC. Then we are tapping the load from the AB, that is from the main transformer. This is one phase. That is what I am calling is the phase number 1. Then the another phase we are getting between CD. The voltage across the load is V2 here. Here the another phase, that is between C and D. This is phase number 2. Then the voltage across this load is also V2. That is, V1 is the primary voltage which is three-phase in nature, whereas the V2 we are getting a two-phase voltage across the two windings of the secondary of the main as well as the teaser transformer. The current which is drawing in the secondary is V2M, that is, it is a main transformer secondary, therefore it is represented by I2M, whereas the current which is delivered by the teaser transformer, that is represented by I2T. This is how we have to draw the circuit diagram for the T connection. It is very simple. Start with the main transformer, then you connect a teaser transformer, then you have got a ABC. To that ABC of the primary you have to connect the three-phase supply. Then you are getting the output from the small AB and CD of the main as well as a teaser transformer. Okay, these are the voltage and current. For this we will draw the vector diagram now. Now three-phase supply, which is the supply we have got as from the three-phase supply, we have got three voltage, that is between A to B, B to C, C to A. They have got all equal magnitude and their phase displacement is 120 degree. Therefore, I am representing here this VAB, VBC is 120 degree apart. Then VCA has got lagging VAB by another 120 or plus 120. One and same. The same thing I am putting in the closed form. It looks like this. There is voltage on the transformer primary. What is the voltage across the primary winding? That is between the main transformer as well as the teaser transformer. So that what I am doing here is I am making closing the vectors in such a way that I have got AB I am taking here. Then I will slowly take VBC. Then I am taking VCA here. Then it is a closed vectors, that is VAB, VBC, VCA. The same vector diagram I am reproducing here, that is the voltage which is across the primary winding of the main transformer. We are looking into the transformer here. There is a voltage AD between the primary winding of the main transformer and also it is a BD. The total voltage between AB is V. However, it is at the center tap the voltage across AD and BD have got half of the V1 or the line voltage, half of the line voltage. Then the voltage which is across CD is, it is 86.6% of the total voltage. That we'll see in the vector diagram. Same thing I am showing here. That is what I am taking here is, it is a VBC, VCA. Here I am dividing, that is the voltage between the AC, sorry, that is CA, that is AD, that is AB. AB can be divided into AD and BD. Therefore, it is AD and BD. Therefore, the total voltage from here to here is VAB. The VAB is divided into VAD and VBD because D is the center tapping point here. It is center tapping point here. Therefore, the VAD and VBD is half of VAB. Then the voltage across the CD, that is the primary voltage across the teaser winding, that is this is CD. Then how we are getting this? Now this is VCD. How to get the VCD, that I will derive there. Just you have to remember that how to draw the vector diagram. That is, we have a BC here and CA, that is a full vector. Then this VAB is divided into VAD and VBD, and at this center point we have got a VCD, that is a voltage across the primary of the tracer winding. At the same time, across if you are connecting a lagging load, then these are the lagging load, that is the angle of lag is phi here, it is 30 plus phi. Here we have got a 30 minus phi, the value of the current IA, IB and IC we are getting. Here there is a change in the phase angle with respect to the different voltages because of the two transformer you are using, and there is a phase shift of one is 30 plus phi, the other one is 30 minus the phi. This is the current vectors of the primary. Then if you are looking into the secondary winding, if you are looking into the secondary side, then if you have got the two voltages, that is V2, that is a voltage across phase number 1 and phase number 2. Here it is a two phase, therefore the phase displacement with the two phases is the 90 degree. Therefore it is V2 and V2. One is across the main, the other one is the teaser transformer. Then if you are taking a lagging load, the current lags the V2, this is the teaser transformer. Then it is I2M, which is the current of the main transformer which is supplied to the load. It is lagging an angle of the phi. Then I am marking this as VA, A, B, C points. Then I want to derive the equation. We know that from this triangle, that is VAB is the line V1, that is nothing but the line voltage, that is taken as a reference. VBC is also VN, it is a balance supply applied, but the phase displacement is 120, that is minus 120. Then it is CA, which is leading VAB by 120 or lagging 240 degree. It is one and same, that is VCA is equal to VL an angle of 120. Then with this background, just I want to see here the voltage VAD, that is this voltage VAD and VBD are equal and they are in phase with VAB, because the VAD and VBD is part of VAB, because these VAD and VBD are in phase with VAB, because VAD and VBD are half of the VAB. Therefore, VAD is equal to VBD is equal to half of VAB, that is what I am putting here is half of VL an angle of 0 degree, because the VAB were taken as VL an angle of 0 degree, therefore it is half of VAB, that is VAD and VBD, that is half of VL an angle of 0 degree. Then the voltage between C and D, that is the voltage across the tracer winding of the primary winding. Then what is that voltage VCD? The VCD is nothing but it is VCA plus VAD, that is VCA plus VAD. That is VCD is equal to VCA plus VAD. It is a vector sum. Therefore, we know that VCA, what is the VCA? VCA is VLN angle of 120. Then what is the VAD? VAD is half of VLN angle of 0 degree. That you have to substitute here. That is, I am substituting for VCA from here, that is VLN angle of 120, and VAD I am substituting from here, that is half of VLN angle of 0 degree. Therefore, what I am getting here is the voltage across that laser winding is not full voltage is available, only it is 8.86 times of the total line voltage. That is why you are making the tapping of the primary winding is 0.866 times the number of turns of the main transformer. The three-phase transformer has the primary voltage rating, that is root 3 by 2, or it is 0.866 times the voltage rating of the main transformer. Then the voltage VAD is applied to the primary of the three-phase transformer, and therefore the secondary of the voltage is V2T of the three-phase transformer will lead the secondary terminal voltage of V2M of the main transformer by 90 degree as shown in the figure. That is, it is quite evident. Here it is a V2T is leading V2M by an angle of 90 degree here. These are some of the important points regarding the transformer. That is a Scott connection. The transformation of the main transformer is K is L2 by N1, whereas the transformation ratio of the three-phase transformer is it is N2 is a full winding in the secondary. However, in the primary it is 0.86 times N1, therefore it is 1.15. Some of the applications of the Scott connections we know already, that is the Scott connection is used in the electric furnace installation where it is designed operate two single phase transformers together and draw the balanced load from the three phase supply. In that case we are using the Scott connection. It is also used in the electrical tail which were started with the single phase load, but however the input is a three phase supply. The Scott connection T connection is used to link a three phase system with a two phase system with a flow of power in the either side. It is make use for converting a three phase to two phase or two phase to single phase. These are some of the application of the Scott connection or T connection.